Okay, our second speaker is Vincenzo MANCUSO. The Italian participants. No? He got his PhD from Palermo in Italy, and I will say here in New York, and Rice, and is currently a research associate professor at IMDEA of India. Pronounce it that way. In Madrid, and is working on analysis design, experiments, wireless and intelligent edge architecture for communication and computation.
Thank you very much. Thanks for the kind introduction, and thanks François for inviting me, and Andrea, and thanks a lot to Anna for organizing.
I wanted to.
There's something in front of the.
Yeah.
Okay, maybe you can just exit.
I did it, but. Okay.
Oh, no. Okay, now it should work. So, right. So today I will talk about edge-assisted platooning, in particular about the control and optimization of platooning when it moves to the edge. This work has been done in IMDEA Networks. There are many ways of pronouncing the name of my company. Many people say IMDEA, some other IMDEA, doesn't matter. Call it whatever you want. But also in collaboration with some other people from Italy, from University of Milan, Politecnico of Torino, University of Trento. I'll show you the names later. So the idea is that one day at least we may relax and platoon on the highway or in the city, whatever, without having to stress too much about driving. And so we may stay comfortable, at the same time use better the road in a more compact way, more efficient way. We may save fuel, so we may have a reduction of carbon footprint, of expenses, all this nice thing that may lead to potential large markets in the next future. But not just for car manufacturers, of course. But the traditional paradigm has been to run platooning on vehicles without the support of the edge. But our proposal is to go one step beyond and move the control towards the edge of the network, considering that you can have not just one platoon, you can have many platoons to coordinate. And this can be done with the help of the new features of cellular networks. And the slide I have 5G, 3GPP, ETSI, which are the players of this change that we are witnessing in these years. Although what really matters here is to have a cellular network with efficient access, wireless access, and some computing power at the edge of the network, close enough to the cellular network. So it may apply as well to 6G or to whatever next cellular network you want to invent or whatever will come. This way, using the access plus the edge, the idea is to avoid the limitation of vehicle-to-vehicle communications, which are intrinsic in the locality of communication of V2V. A thing that, of course, will be important, as we saw also in the previous talk, is machine learning, the way dynamic arrangement, so decisions about how to compact a platoon, how to move platoons one with respect to the other is going to be done, is something that can be learned in the network. There are many problems that can be dealt with when we move the control of platoon to the edge. So first one is, okay, is it really possible to do that? That's the first question. Will it work? And we did actually propose in a paper a framework for MEC control platooning. You can read it as edge control platooning, but we thought in particular to the MEC of 5G and to the features of virtual functions of 5G. But again, that's just the context in which this was developed. And then we do performance evaluation by means of simulation. This is the main types of what we did. This way, we will have a platoon of cars or vehicles, commercial vehicle, whatever, that we assume to be homogeneous. And the control will be very close, but it will be in a virtual network function in the Mac, Mac app if you want. Problem that we found is that at some point the network delay may be too high, and then you cannot really do that. Okay, so the message is it can be done, but with some caveats. There's another problem, which is what about when platoons, when there are back-to-back platoons or platoons get too long that you can really sustain them, and you have to split them in sub-platoons. So we extended the framework using the Mac in order to control this kind of platoons of platoons, if you want. And I'll show you a two-tier architecture with controllers and another virtual function that coordinates multiple controllers. Problem in this case is there are some limitations because there is other traffic apart from your platoon. So if you have a long platoon or you have many platoons back to back, anyone else may not use the road as he wants because it cannot pass through the platoon. I mean, it's like a big convoy, and what do? You wait forever before you can exit or take a right or whatever. That's a problem. A third problem that we addressed, I don't really know if I will have much time to show you what we did for this case, is since we need computation, it's really where we do the computation. I said edge, I said Mac servers, Mac hosts, but in a network, we are supposed to see in the near future a number of Mac hosts, a number of edge devices. I think Falco yesterday said, in reality, they are installing a very little number of Mac edges. So for the moment, this is not a big problem. You don't have many options. You have resources in a few places, you pick that and use it. But in the future, the idea is that you have a Mac host behind any corner, basically, behind any base station. I don't know if this will be true any day, but that's the idea. For that case, you may have a lot of load for this host, which will be very tiny. And you may want to migrate the virtual functions that are controlling the single platoons in a way that allows to have enough computational power for the platoon where you need and when you need. For this case, we will use a control of migration of virtual network functions using machine learning. Problem in this case is learning may be slow. And so we also propose some mechanism in order to do with very low overhead, a kind of federated asynchronous learning. But let's go step by step. So step one is about the single platoon. So single platoon operated through the control function that runs on the edge of the network, or edge-assisted platooning challenges. The traditional scheme of platooning, just in case some of you may not remember it fully, is based on V2V. We have a platoon leader and a number of followers. The information about the followers are sent to the leader using V2V. Eventually, this can be also done with multi-op transmissions, but it's better if you can do it in one op because there's more delay in multi-ops. And the platoon leader, so in the platoon, in each car, actually, there's an onboard unit in which there are two layers. One is called the coordination layer, the other is the actuator. The coordination layer will compute a control law, which tells which acceleration should be used by the vehicle in order to keep the pace of the rest of the platoon and then maintain the distance, to adjust to possible variations of speed of the leader or any other user. There's an actuation layer because the system is mechanical. There's some echo. Oh, okay. So when you are running a system, a software system, and then you tell a mechanical system to actuate, there could be some delay. In the case of cars, this delay may be high. So this has to be taken into account. I'll show you that it has a strong weight in terms of performance. Then in traditional case, what is done is to use 802.11p protocol or variants. There are LTE 3GPP versions of V2V communication protocols, which are similar in nature, but they don't really use the base stations. They can get support from the base station in case of LTE. What we propose is quite different. We have the same vehicles, leader, some followers. Each vehicle transmits to the base station the current status of the car, so the speed, the acceleration, so that they convey the information about the motion of the car. The base stations will relay the data to a MAC host. In the MAC host, there's a MAC app, which is a virtual network function. This virtual network function is running as a kind of digital twin of the platoon running on the VNF. It runs a control law and issues the control information for the cars. So here, there's involvement of the onboard units of the car, the radio access network, the backhaul for communication to the MAC host, and of course, the edge, the MAC resources itself. Is it better? It is worse than V2V. Of course, it requires infrastructure, while V2V does not. So that's a price to pay. It's a centralized version of control, while original control platoons is thought to be distributed. You may like it or not. Depending on the application, one thing may be better or not. It's not using the radio in a non-controlled way, so it's using a scheduler. So this is an advantage of using the base stations. What happens if you consider the size of the platoon, the way it scales? Of course, if you have to relay on multi-op transmissions, you cannot go forever with an endless platoon. While if you have a relay on base station, you may even have some cars connected to a base station, some other cars connected to another base station. As long as the time to reach the MAC host or the round trip time car to MAC host is small enough, doesn't matter. Huh? So this scales much better from the point of view of size of also, the transmission communication, the channel communication of the communication is better for base stations, or at least it's more uniform and more homogeneous, I would say, for all users, rather than what can happen if you have to talk with a car in front of you or with two cars in front of you, 3 cars behind. So a condition may be quite heterogeneous in that case. The other advantage of this approach is that if you have an intelligent transportation system implemented in the network, then it's much easier to coordinate with that because you are already in the network. You can have virtual functions that can talk to each other, sharing information databases and whatever, thanks to the service-based architecture of current cellular networks, then you can coordinate. If you go for a VANET or V2V approach, of course, all of this is lost. So back to the proposal, this MAC host with a virtual network function inside. What is this implementing? It is implementing the classical cooperative adaptive cruise control law, which is the most famous and most used platooning control law. And for each vehicles, this control law is computed based on the information of the vehicle itself and the preceding vehicles. So VI is the target vehicle, information from the target vehicle. VI -1 is the one in front. And in this case, we also need V0, which is information about the leader of the platoon. Having information about myself, the one in front of me, and the leader of the platoon, CACC will tell me what is the acceleration that I should instantaneously apply to my car in order to keep my position and my relative position distance to the other cars in front and behind me. So this means that in practice, for each vehicle, the controller can compute the control law asynchronously. There's no need to do it once you have all the information for all the cars, which helps in terms of scalability, because if you just depend on yourself, the one in front, and the leader of the platoon, anyone else, doesn't matter if 1 or 100,000 vehicles, are not of importance for you. So this can be done, and it is implemented the way we did with the synchronous update messages sent from each vehicle to the controller and from the controller to the vehicle. And in practice, we have this dependency graph. This dependency graph means in each node is a vehicle. And then if you have an arrow, for instance, there's an arrow from V2 to V1. This means that V2 depends on V1 because it's the one in front. You may invert the direction of the arcs and read the same information range. But let's look in terms of dependence. So what happened here? That in this graph, if there's this graph tells you that if V1, for instance, is sending an update about V1 reaches the controller, then V1 itself and V2 have to be updated because they depend on V1, both of them. Each one depends on itself, the one in front and the lead. So counting the number of arcs in this graph as the property that tells you how many updates for the controller you need in the network per update cycle. So it's probably a stupid graph, but it's easy to visualize the complexity of the mechanism. So based on this, actually, we found that the number of, if n is the number of vehicles in the platoon and phi is the frequency of updates that you send, then you have this phi u times 3n minus 4, which is the number of updates per second, or if you want, number of computations per second that the controller has to perform. To make the long story short, so in the end, what we do with this architecture that we propose, we simulate it realistically using Sumo for mobility. We built on top of Sumo. We built the cellular environment and the Mac environment on top of by synchronizing basically a new simulator on top of the Sumo mobility simulator. And for what concerns the network, we do a simplistic approximation, which is about the delay. The key thing here is to understand if the controller has time enough to receive updates and send updates to the cars before cars basically run out of control. Or they may crash. If they have to brake, they have to brake on time, and so on. So what we do with that, we say, okay, let's assume that that this delay is a random variable. And let's analyze the performance of this system considering different distribution of the delay in shape, from uniform to exponential log normal, or other shape, and also in terms of the parameters of this distribution. And very important one is the average. We also account for the fact that there's a delay in actuating the control or whatever is issued by the control. And actually, we can disable this delay and see what is the difference and what is the weight of having a mechanical system to be integrated with the software system. I'll show you some performance of what we have. First of all, stability. One of the metrics used for platooning is the string stability, which means that if you move from the head of the platoon towards the tail of the platoon, you want to see errors in the positioning, the target position, that goes down monotonically. So in practice, the most vulnerable vehicle in a platoon is the second one. It's the one that can suffer the higher positioning error with respect to the others, if the platoon is string stable, of course. It's a nice property because then you can focus on making safe the second car, and the rest will stay safe. That's the idea. This graph was colorful. It shows different values of average round trip time between the cars and the controller, from 30 milliseconds, which is something that should be doable in an edge environment, to 220 milliseconds, which means that you are not really in the edge, but you are probably already in the cloud. Maybe a close cloud, not so far, but it's already a cloud level. And you see the first three cases with blue, orange, and green. This represents the absolute distance error. Okay, so it's in meters when the target distance is 10 meters. So this is a fraction. There are no accidents. This is the absolute error stays in distribution because this graph represents distribution, well below the 10 meters that guarantees no crash. And you see a trend towards attenuating this distribution, the mass distribution of the error of the target distance as you move from the head of the platoon towards the tail of the platoon. When you get to 220 millisecond delay, that's not exactly true. So which means that at some point, if the delay becomes too large, you may lose string stability, which complicates a lot the management of the platoon. But for less than 100 milliseconds, this is okay. And 100 milliseconds is not such a complex target to achieve in an edge net. In the previous graph, I was just considering the distribution of delay. Now, you know that in the network, you may even have some packet loss. Should not happen in cellular network. You may be able to recover, but what happens if you have some percentage of loss? Sorry, that was the other slide. So this one is actually I was not looking at the slide. So what is the impact again of the error when you have when you increase the mean more finely? Before I was going with steps. So you go from 30 milliseconds to 220 milliseconds. The absolute distance grows a little bit. The distribution of errors starts spreading a bit. The type of distribution counts a little bit, not so much. What really counts is the way the leader, the platoon leader, moves and accelerates. This graph and these dots in the plot are referred to that speed profile, which is a realistic one taken from some realistic data. Okay, it's someone driving or in the highway. Actually, there's some speed goes to 120 kilometers per second. So with that profile, you see the absolute error is below a meter, below half meter, with target of 10 meters. It's super good. If instead you take a case in which the leader starts doing crazy things, which is going with the speed that changes sinusoidally, the error becomes higher, much higher. Not so high in the end, it's 1.25 meters, but it's much more. The sinusoidal acceleration and velocity profile is something which is often used when evaluating the performance of platoons, because it's really harsh for the system. Okay, so if you can cope with that, you can cope with the rest. That's the idea. Okay, so if you have errors, what happens? If you have error, you may miss some packets and recover soon after. Okay. There's an extreme case of error. Imagine you enter in a completely not served area, so no cellular network for a few seconds. This is the case, for instance, that there's a profile of speed which is represented in the small box, and this is done for a blackout of connectivity of several cars while they were braking. So this shadow area in the middle represents the simulation time during which some of the cars of the platoon were in the blackout area. Each color, each line represents the gray one is the speed of the leader, and the other lines represent the distance from the preceding vehicle, which has a target of 10. So you see, before entering the shadow area, the target is 10 meters, is basically respected with very small variability. Inside, you see that everyone starts going in a different direction. It is not that bad, because here, after 13 seconds, there was no crash. I mean, the target was 10 meters, and the worst case is this one, this blue line, which is the second vehicle, of course, the first follower, that gets 7 meters away from the leader. Still a lot of space, at least safe enough in order not to crash. Of course, if you increase the time during which there is no coverage, at some point there will be an accident. Which means that this Mac-based approach may be safe, but you always need a backup solution that you can switch to rapidly. And this is actually ACC, which is a non-cooperative version of CACC, relying only on V2B. That's doable. Actually, we did also that. I see strange messages here, but you don't, so it's fine. And I mentioned before about the actuation layer. So here I have a heat map on what is the downlink delay. So on the X, we have the delay in downlink. On the Y, the uplink delay. Total delay is the summation of the two, assuming some distribution. And the heat map represents the error, the quantity of error in meters. So half meter or less. So here we reach up to 70 centimeter error with respect to a 10 meter precision in this example, if we don't have actuation delay in the mechanical part. If we introduce the mechanical part, we have the table on the right. You see, the heat map is hotter. In practice, the presence of the actuator layer that works more or less like a low pass filter on the instruction received from the controller is more or less equivalent to add 50 to 70 millisecond delay. It's not small. It's an important fraction of the budget that you may get. So it has to be taken into consideration. It cannot be neglected. That's a mess. From a point of view of what you can really do with this in a network, suppose you have 50 vehicles. Suppose you want to update 10 messages per second. The frequency at which you send messages is important. And each message is about 200 bytes, which is more or less what is needed for CACC to control. It's not much data. It's less than 1 megabit per second for a platoon. And in downlink is a bit more because you have also the control instructions. It's 2 megabit per second. It's not much. This means that also in terms of computation, it's a few thousand computations per second. Easy to do because it's really super easy to run the control law. These numbers are tiny, which means that considering the number of cars that you may have within the coverage of a normal cell in a network, there's no problem. Absolutely no capacity problem. Even if the cells are quite large. So, of course, if the cells are small, you probably don't fit enough cars in the cell. Then you have another limitation. But I mean, this is more than enough to have tens of platoons under the control of the same MAC host, if the MAC host can be devoted to the traffic in a cell, of course. So the answer to the original question is that it is basically doable to do platooning on the edge with traditional like control of platoons like CACC with some modifications. The distance error is typically a small percentage of the target distance between cars, so it's okay. You have to account for not too high delay in the network and route trip time in the order of the 100 milliseconds or so. You have low requirements on data rate and CPU, so it's scalable. And eventually you get good efficient management of even long platoons in this way. But how long can you go? That's the second step. So consider this. You have the platoon manager in the MAC, and this platoon of commercial vehicles connected to multiple stations. So they may have different delays, of course, which is a problem. Each one has a different distribution of delay. Not only this, you may have other cars that want to cross the platoon because there's an exit. They cannot. They simply cannot. So if the platoon becomes too long, we need a mechanism that splits the platoon and rearranges the platoon depending on the physical condition of the road, of the traffic, of the cellular network, and so on and so forth. This leads to what we call multi-platooning, the organization of multiple platoons. we did the study for an intersection, for a junction in the highway, but this can be done also for a roundabout or for any other cases in which you have other traffic that wants to flow through the platoon. So in practice, the idea is, okay, let's do multiple platoons and leave some gaps in between each subplatoon through which other cars, other vehicles can pass. How do we do this? Each subplatoon is managed like I showed before for the single platoon. So it has a virtual network function in the MAC, which is the platoon manager. There's a second step, which is to coordinate these different platoons, because you want to keep some delta distance in between each of the platoons. But then logically, this is like a platoon of platoons. Then the multi-platoon manager can see each of the subplatoons as a single vehicle. And we can actually duplicate the architecture that they showed before, also from a point of view of dependency. So if you have a single platoon of 9 vehicles, you have this dependency graph, which is the same I showed before for just longer platoon. If you group these 9 cars in 3 platoons of 3 cars, you have 3 subgraphs, 1 for each subplatoon, and then you have another graph, another dependency graph, which is a dependency graph between platoons. The rules are like before. So the number of updates depends on the number of arcs that you see in this graph and so forth. This leads to compute the number of operations, the number of messages that need to be sent by using a single platoon with a single controller or a multi-platoon with a 2-layer architecture of controllers. When you have the 2-layer architecture, some information is lost because the multi-platoon knows where the head and the tail of each single platoon is, doesn't know anything in between, which means that within a single platoon, you have to rely on the local, on the low-layer platoon managers to make sure that there's string stability, while the multi-platoon manager will have to deal with less messages. In general, there could be a reduction of the number of computations per second in total to be performed and the number of messages to be used. Where is the price to pay? You have traffic in the backhaul, because now you have traffic in between VNFs that they have to talk with each other. Does it work? Well, also here it depends on the speed, on the delay that you have in the network. This graph, in this graph, each color is a different number of subplatoons for a case in which you have in total, I think, 20 cars in the same platoon. So the string stability is the error versus the number of the ID of the car from the lead to the tail. You see there's string stability preserved in the first case. The first case is a case in which delays are small. The uplink plus downlink is 30 milliseconds in round trip time. And there are 10 extra milliseconds in between MAC hosts. Okay. If we go to another extreme case in which we have 120 milliseconds to reach from the MAC host that controls a single subplatoon to the multi-platoon leader, then in that case, the string stability is a bit compromised, which means it's important to keep the multi-platoon manager close enough to the subplatoon managers. It is actually, I don't show it here, but it's actually more important to keep the VNFs close enough, packed enough, rather than keeping the single VNF close to users. That's more important. Okay, but what can we do with that? Many things. One is, for instance, consider that there's a utility behind the compactness of a platoon. How can we measure that? So we can give an expression of this utility and then try to use it to optimize dynamically the composition of a multi-platoon. We come up with an expression of utility which is easy, it can be modified easily as well. The idea is that the utility is a sum of components. So it's the logarithm of a product. So it's in the end a sum of logarithm elements, in which we have the kind of reward, which is the road utilization, this R of T, which measures the compactness of the platoon, so number of cars per meter, if you want, normalized to what you would have without in a normal deployment in which you cannot platoon. We also have gas utility, energy utility, because platooning, thanks to the drag effect, allows to save gas in the cars that are following the leader, typically. Also, the leader saves something, but especially if you are following, you have this drag effect that reduces the friction, and then you have to use less energy to travel at the same speed. Each car, depending on where it is and what it does, will have a different rewards in these terms. And this is the term in green in there. Costs are in terms of computing in the network and transmissions in the network, which are the red part in there. Also in those cases, so for all these cases, we do normalization of each element to what happens if you cannot have the platoon. Okay, so we have a reference point, and we avoid some strange behavior of this logarithm function. Okay, that's the utility function. Typically, you have a utility function. You want to do some optimization, you need a constraint. So easy. I want other traffic to flow through my platoon. Let's say that beta is, or vita, as Americans say. So vita is the intensity of traffic that wants to flow through, and assume that P is the intensity of traffic that can flow when there is a gap, a meter of gap. Then you have to balance this thing with the length of the platoon, the number of gaps, and this gives a minimum value of the gap. Of course, the larger the gap, the better, more traffic can flow, which is a constraint you want to respect when you decide how to split the platoon. The platoon of NV vehicles of length L, spaced by delta, will be delta small delta, will be split in NP subplatoons, such that this capital delta will be limited by this number, the lower bound. This means that if beta changes, delta changes. So if delta changes, reorganize the platoon. Okay, what we do if we want to reorganize? I tell CACC that I want to move the target distance between some users. It's a problem. If I tell all of a sudden to CACC to move from a distance of 10 meters to 50 meters, the distance the car will respect goes like this. Adjust gradually when I get those curves in there. What is the problem here? There are two problems. One is that different cars will do different things. And the second is there's a tail, which is delay. Why is this a problem? Because I want to reorganize my platoon before getting to the point in which I have a different value of beta. So I have to be ready on time. And if I have a tail, that's something that may cause some trouble in the network. So it seems that using CACC this way doesn't really work. What we found is that a more clever way to do it is analytically by imposing to CACC a soft change in the acceleration pattern of the vehicles. It can be done with basically many types of zero mean average over a period of acceleration. We did it with one period of a sinusoid. This is the case in which you first brake and then you reaccelerate because you need to reach the same speed before and after the maneuver in order to keep going. But if you first brake, then reaccelerate, you basically open a gap with the one in front. If you do the other way, you close a gap. It goes the same way. And the only thing that you need to do is to compute for each one of the users, which one is the acceleration module of this sinusoid thing. And the result is, analytically, believe me, I don't have time to show it and to give all the results, that within the same t, which is a period of this sinusoid, you have changed the configuration of the platoon exactly. Let's say with small noise, okay, in reality. So this worked very, very, very nice. What happened then? Okay, if you consider the utility function of a platoon, without changing beta, which with beta equal to 0, which is the ideal case, you find that most of the utility comes from the gas saving. Okay, this is the orange bar, and the gray bar is the total utility. So you see that it's basically that one. The other important thing is that the most convenient configuration is that we have a big packed platoon. It's normal. It's more packed. There's more drag effects, so you save more. But this is with beta equal to 0. If you move to beta, which changes, what we did was consider a case in which you periodically have an intersection, so you have to leave space to the other cars. So you have a value of beta that goes from 0 to a non-zero value and back to 0, and then again to the non-zero value. What is optimal? This can be searched with some tricks, but it's numerical search. And we obtain this kind of graph. So as the intensity of beta with respect to what is the permeability of the platoon in the gaps, the speed factor, increases, the utility goes down. And this is the average utility, of course. And the number of subplatoons to be used inside the junction or outside the junction is optimized in a different way. These are the two curves here. Of course, the higher the intensity, the higher the number of subplatoons that you need to have, or the more you need to split the platoon when you get into the intersection. The last message I have is about who is gonna gain out of all of this. This plot represents, we saw that is mostly because of saving energy. Okay, but who saves energy? If one is the energy that you consume if you don't platoon, and you look at a specific case with beta over p equal 0.5, but it's similar in the other cases. This is a case in which out of the platoon you have one big, out of the intersection you have one multi-platoon. In the intersection you split into 4. Okay, this is what the optimization says, with some distance which is 93 meters and with some peak acceleration, which is another output of the optimization. Then the leader is the one who saves less. The users which will become leader for a while during the intersection are the one that save enough, but not as much as all the others. The tail of the platoon is also not saving as much as the others. So, and the line is the average. We have a model and simulation here together just to show that it works. The thing is it fair? It seems like we should study something else, which is also kind of rotation within the platoon to be fair to the users. Huh? But this is the last piece of message. So just to wrap up, we managed to have this architecture that we call Plato, by the way, I didn't mention before, for platoon, multi-platoon control. It is very efficient in terms of computation and communication overhead. It has embedded this reconfiguration, analytic-based reconfiguration of platoon, which result to be quite smart, and manages actually to preserve stability within some delay of the network. Compact platoons tend to be convenient, but a bit unfair. This is the thing. I will not talk about the edge control and the machine learning because there's no time for that. And I basically thank you very much for the attention. Just let me mention a few names of collaborators. Sorry if I skip this part here. Marco Aimone, my student Constantine, and Paolo from University of Trento, Valerio, another student in Milan, but also with me in Madrid, postdoc in Milan, Cristian Quadri, who developed part of the simulator, Gianpaolo Rossi in Milano, and Michele Segato, who helped us with a lot of things related to Sumo, and CACC is one of the authors of CACC. So thank you very much. Thanks for your attention, and I'll be happy to take questions. Thank you.
Questions?
Yeah. So it seems that the computation needed in the edge is very small. I mean, is it something like Arduino can run, or maybe
for a single platoon, maybe yes, but the problem I didn't show it was I knew I didn't have time to show that, but the third problem I addressed is exactly about that. If you have a background load in in the Mac servers, and you have to run also control of platoons. How many platoons can you really control? This changes over time. And in reality, Arduino is definitely not enough. The single platoon requires a few thousands of computations per second. This is a tiny number. But if you have a Mac server which is quite loaded, you may have some delays in doing the computation. And this breaks the safety of the platoon. So you cannot really do it.
You have a dedicated Arduino
If you have a dedicated slice, yes, you can do it. But even there, you may need somehow to migrate the virtual function, because as the platoon moves, you get away from the point in which physically the computation is done, which means the delay may change. Okay, so there's space correlation to be taken into account.
Right, and this you don't have result about this platoon that changes, and so the control.
On this I have a paper, and I also in presentation I have some slides there.
Jumping from a Mac to another.
Exactly. Yes.
I would be curious to know about this.
Yeah, no, I can show you. Probably not now, but please.
So just to understand, so finally, the power is very low. There's not much data to process it. Okay, so they just to understand, it's interesting. In the case there's no V2V is possible.
It's interesting in the case you want to have a centralized view of multiple platoons, for instance. For the single platoon itself, the advantage is when the platoon is too big. It's too big, and the delay of V2V becomes above the 150 milliseconds, which may happen, or also you have to combine delay and packet loss, which are common in V2V, and they are not common if you use base stations. So it depends. If you have 3 cars, probably you don't need all this thing. If you have 10 cars, probably you don't need this. But if you have 20 groups of 10 cars, you need it.
Now, I find it quite interesting because platooning is one of the applications which has quite strict requirements, right? One of.
Right.
And then if you can say that, okay, we can handle everything at the moment, then we can say same thing to the collision avoidance applications and other applications that we traditionally said that we need V2V. But then if you say, okay, we can handle everything by Mac and so on, then okay, let's get this tightening communication away and everything can handle by the cellular. Are we going to get this conclusion finally?
No, not really. No, in my opinion, no. We are going to get an hybrid system. The V2V is definitely very useful as a backup system, for instance. Yeah. And for safety, you need it.
Yeah, yeah, that's the classical.
But not only.
But that's what we think. That's very intuitive. That's the big question is that okay, the automated going to deploying this V2V technology. Because it's costly. If it's only for collision avoidance, who will take the responsibility of all of these things? Where is the
there's no big incentive at the moment.
And so on. Then okay, if you say okay, there's not much economic benefits, and okay, the car makers interested in platooning, you can handle it with Mac, with the vertical communication, and finally, I'm wondering if it's the if we go into this direction, that is quite surprising, but it's interesting to know.
I mean, it's surprising, but there are a lot of details that there was no time to present. In a real network, how do you really guarantee that the service is working continuously? If the network stays like it is, probably you cannot still trust it. If the attempts to go for deterministic networking will be successful in the next few years, and then you can really guarantee some millisecond delay in the backhaul and millisecond delay in the access guaranteed, then you probably don't really need the V2V.
Because you're saying it's platooning, the delay requirement is much stricter than the collision avoidance applications. alert. And so,
Depends.
okay, we can use platooning, then naturally we can say, okay, well,
You can.
why don't we use the original specifications? Then what we use for me to define it?
A good question, but well, that's it's a political question.
It is linked to this discussion. So when you study this RTT, you had first the uniform on which is bounded above, right? And then you looked at other cases,
We look at, yeah,
exponential,
and log normal.
okay.
Yeah.
But I don't understand if there is no upper bound.
Mhm.
The RTT is individual, right? So it's to a given car.
Right. Yeah, yeah. It's a distribution, so you're
Yeah,
right.
so
It may be
if it-
very high.
If it's unbounded, then
Doesn't matter.
you get the information, say, with
Uh,
probably very small.
There's a trick. There's a trick in there.
But then how can you avoid a crash, right? If it's unbounded? I don't
You
understand.
keep sending updates.
Sorry?
You keep sending updates. In the results I show you, I send an update every 100 milliseconds. So whatever comes from the distribution, which is above 100 milliseconds, means that I lose the packet.
Okay.
It's like I lose the packet, but I have next packet that compensates. That's the thing.
Okay, but there is still a small probability that, I mean, all of them exceed.
There's a small probability of them exceeding, and that's a blackout case.
Like when you
But-
have Andover.
When and over is not seconds, it's pure.
From a Mac to the other one. You are expected to have a spike.
Right, right. That's part of the other work I didn't show today. We consider that, yes, exactly. But I mean, Andover in the Mac is in the order of subsec. Okay,
Okay.
so it's not taking a lot of time. Assuming that you have a virtual machine ready to adopt the status of the other virtual machine and run it. If you have to wake up a new virtual machine, then you may have a problem. Okay, but the key thing is the frequency updates of messages that compensate for losses.
Right.
Yeah.
But you take them independent and.
We take them independent. The moment we
but
take
that
the
bad channel condition would perhaps be.
again, the
problematic.
blackout case is
Yeah.
not independent. All cars
Okay.
get in the same condition with no channel at all.
Mm.
Okay,
And-
which is an extreme case. Of course, I have the case of full independency in the paper and so on and so forth. But the more complicated is this one. Yeah.
And another question. So I read that the gain in consumption goes up to 20–30% for gas consumption, but when vehicles are very close, like
Few meters. No, within up to 10 meters.
10 meters.
It depends on the kind of vehicles.
Oh yeah.
If it is a small vehicle or a truck, there's a huge difference.
I see.
With trucks, with this commercial transport trucks, you can have a gain of 15% when you are 100 meters away.
Oh really?
Yeah, in the highway, of course.
I see.
If there's no lateral wind or thing like that, up to.
Any other question?
Yes, I have a small one on the same line of what we were saying before. The other solution could be, since in the single platoon, the controller is the same that they are using in the edge. It's the same that you are using in the platoon when you are not using the edge.
Yeah.
Why don't you use both?
It's not exactly the same, to be honest,
Okay,
because
so I use that.
because this is one controller centralized, while normally you have a local instance of controller in each car, in the completely distributed version of it.
But if they run in parallel, if they are fed the same data, they should give the same actuation.
With different delays, so
with
similar.
different delays.
They should be similar. You can run them in parallel. Yes, you can run them in parallel. It's yeah.
Yeah,
It's a
okay.
possibility. It's a
I agree,
possibility.
doubles the cost and-
Or you want to have two channels in parallel and you pick whatever is available. Doable, yes.
If we take in the silence periods, like the V2V thing will.
Again, I'm sorry I couldn't show it. I have another mechanism which is based on machine learning that learns that if the delay comes above a threshold and the Mac load is some kind, may even decide to switch to distributed control. I have it, yes.
Okay, thank you very much.
Thanks.
take a 20-minute break.